Thank you, and welcome, and thank you for coming. It's been an impromptu seminar, not a whole lot of notice, but we're very happy to have Dr. Luca Turin here at the University of Alaska Southeast. Some are hosted by the biology program here, but I'm going to say mostly hosted by Michael Reed-Hunter from Harshside Books. All right. I'm not going to pretend I know Luca Turin. We're both physiologists, and that much I know. So I'd like to introduce Michael Reed-Hunter, and he will give a much more welcoming introduction. So Michael.
I don't know if I can or not, but January of 2003, I was working one day, and this fascinating book came to be shelved, and it was called The Emperor of Scent by a man named Chandler Burr. And it was about a physiologist, a biophysicist named Luca Turin. And I read this and was mesmerized to the point of buying flavors and scents and all sorts of things through the book. It put me on fire. And I had sent, a little later, I sent Luca a letter and a perfume and didn't hear anything for several months and thought, well, that's interesting, and then got a note back. We stayed in correspondence for a while. And then after a year or so, I finally went to London and stayed with Luca and Dessa and his Adela and Tazio, his son, and had a marvelous time for 2 weeks. That was a year or so ago. And much to my surprise, I mentioned that you should come here at some point, thinking that this is very far away and that would be a nice thing indeed. But lo and behold, I finally have Luca visiting. Now, Luca Turin is an amazing person, especially from the book. He's written his own book now called The Secret of Scent, which further clarifies the original book that Chandler Burr did. And it's an amazing story that he's going to tell you tonight about two theories of smell and his new theory that he put together from an overwhelming curiosity and training in any number of areas. And he brought all this to bear, and with a series of fortunate events and brilliant insights, has come up with a new theory of smell, and that is gradually creating controversy and also creating champions. And so it's an amazing story he's going to tell you tonight, and I'm just thrilled to see this culmination of a friendship. And so I'd like to introduce my good friend, Dr. Turin.
Thank you, Michael. Thanks to everybody for being here. And it's quite extraordinary. I mean, I'm trying to scale up the size of this audience. You know, if you consider the size of Juneau, I shudder to think what sort of stadium they would need if it would scale up to London. You know? And the same thing for the Emperor of Scent sales. We did a calculation yesterday that if there had been a Michael in every city in the U.S., the book would have sold 3 million. Okay? And incidentally, I wouldn't have got a penny, but it would be amazing. So yes, thank you for coming. What I'm going to tell you about tonight is essentially the scientific part of what was told in the book, with a few bits and pieces added because things have happened since Chandler's book was written. Some of the stuff is in the book that I wrote, and some isn't. Feel free to interrupt me if things get unnecessarily obscure. If there's any sort of point that's unclear, feel free to interrupt me. Now, what I'm doing now, I'm very fortunate because I'm a scientist who actually got to put someone else's money where his mouth is, so to speak, as happens with venture companies. Somebody is mad enough and rich enough to say, well, this sounds like a really interesting idea. How about sinking some real cash into this? And so for the last 4 years, I've been actually reducing to practice a theory which is not completely established scientifically. This is a little unusual, okay? It does happen. You know, it happens in the history of technology several times that things worked before people quite understood why they worked, and this is my situation. So what I'm going to talk about is the two parallel paths of reduction to practice on the one hand and the scientific aspects in parallel. Now, just taking the thing from the standpoint of the perfume industry, okay, the perfume industry is an enormous consumer of new smells, okay? In food, I don't suppose you guys would care too much about entirely new smells in food. If somebody came up with a lollipop flavor, you know, that you'd never tasted before, it wouldn't be that attractive. But in the perfume industry, new smells are really the driving force for making more cash. And that's because clients believe that just, oh, at the end of the rainbow, there's a magic material, a magic molecule, which will make people buy their stuff. And historically, it's been true. The big successes in the fragrance industry, chemical milestones, have generated vast sales. Now, there are several ways to get to what are called new materials. One is imitation and development, which is what I would describe as the approach followed by Firmenich, the leaders in the field. There are 6 firms in the fragrance world. Firmenich is the best. Swiss family-owned company, $2 billion a year turnover. Smart people, and they've been doing it in a very interesting way. What they do is they don't try and mess around with second-guessing evolution. They just see how roses do it or how orchids do it. And so they analyze natural materials extensively, and when they find a molecule of interest, they try and make it in ton quantities rather than extracting it from flowers. So that's what I call imitation and development. It's given us things like macrocyclic musks, and which are the classic animal musks. They smell, incidentally, just for the record, musks smell clean and not at all animalic, okay? Don't get any ideas. They smell like clean linen. They're entirely wholesome, should we say. And the damascones, which are wonderfully powerful floral notes. Then there's the hard work approach, and lots of cash. And that's the hapless chemist. And that has worked surprisingly well, considering that it's pretty much a scattershot sort of approach. And people make hundreds or thousands of molecules, and every once in a while, maybe 2 or 3 times in their lifetime, something really wonderful happens, and they take it to the perfumers, and the perfumers, instead of saying, and, say, whoa. And that thing goes to market, and it's sold. And the third way, which is the one that the company I work with is pioneering, is, that's my brain, by the way. So I FedExed it to Susan, and she said it was fine. So what does this tell us about what we know about smell? Well, the first thing, and here I'm telling the story backwards, is that when you have a theory, you don't mess around, okay? So if we could predict smell from molecular structure, there wouldn't be all this sort of hard work chemistry or stealing it from roses or anything. You'd just say, you'd go to your chemist and you would say, give me a big, strong banana with a hint of ketchup. And they would say, yes, sir, and 2 weeks later it would be there. That's what you do when you understand it. So clearly we don't understand smell all that well, otherwise there wouldn't be all this stuff. Now, the classic theory of how odor works is that it's written into the shape of the molecule. This is entirely plausible, okay? The reason it's plausible is that almost everything is connected to the shape of the molecule. Much of pharmacology and much of enzymology and much of immunology and much of biochemistry is predicated on a thing called molecular recognition, which is when a protein attaches to another protein, or when a protein attaches to a substrate, or that sort of thing, where the shape fit between 2 different molecules is what determines the specificity and the efficiency of a particular enzyme or antibody. So the notion that smell should work that way is perfectly reasonable. In fact, it was first proposed not by Amour in 48. This is wrong. It was proposed by Linus Pauling in 1946. Now, the reason why Pauling doesn't get much credit for it is because Linus Pauling used to have more ideas just before breakfast than most people have in a lifetime. And so what he said before breakfast one day in 46 happened to be, hey, I'm sure smell works by shape. And that spawned a whole industry. Okay, that's. And he really couldn't care. I spoke to him about this a long time ago, and oh, did I say that? Yes. So John Moore took that ball and ran with it, and really developed a quite sensible theory of smell based on shape, which was very interesting. The approach was interesting, by the way. He asked people to give descriptors of smell, and the most common ones he figured would be the basic ones. So that his idea was that smell was composed of primaries, like primary colors, and so that if you took the 7 most or the 6 most used words in smell, they would be the 6 primaries. Not bad as an idea, except it never really worked, because once you have whatever, sulfuraceous, camphoraceous, minty, and putrid, and you try and mix those things, you don't end up with bananas. And the 3 at the bottom, Olaf, Rossiter, and Kraft, are professional fragrance chemists. Günter Olaf, one of the greatest fragrance chemists, Karen Rossiter from Quest, and Philip Kraft from Givaudan. And these are company chemists. And this is also interesting because now we're entering a world where it's all corporate information. So the bit that is published is the tip of the iceberg. They publish scholarly papers once in a while where they tell you half the story or 1/10 the story, and then the rest you have to glean over beers. Now, the big revolution in smell came with the discovery in '91 of the smell receptors. Until then, we really had precisely no idea what molecular entities in the nose were responsible for binding to the odorants. And so it was a free-for-all. And if you read pre-91 reviews of smell, they really are an odd collection of wild ideas. Some of them so wild that I can't believe anybody actually sort of put pen to paper on things like that. My favorite is a thing called the penetration and puncture theory, which molecules go through membranes leaving holes. Okay. Anyway, in '91, Linda Buck and Richard Axel, who got the Nobel 2 years ago for this amazing work, discovered that the nose was full, the olfactory epithelium, the neurons, were full of a particular type of receptor related to known receptors, G-protein coupled receptors, and but a very large number of them. Normally, when you have a G-protein coupled receptor, you have one in the particular cell type that's supposed to respond. In this case, in the nose, in total, there are 1,000, actually 347. Now the human genome has given an exact answer. To be exact, Craig Venter, whose DNA was sequenced, has 347 olfactory receptors in his nose. And insofar as Craig Venter is normal, which is doubtful, this is the number of receptors that we all have. So what does it mean? So what was the mindset change that happened when this discovery was made? Well, let me explain what is meant by a receptor. Here you have a schematic protein receptor made of 7 transmembrane helices sitting in the membrane. And you have a molecule here, benzaldehyde, that comes from on high, lands onto the receptor, and induces a change in conformation in the receptor. This animation, like all animations, is designed to boggle the eye and deceive the mind, of course, because what happens in reality is everything is jiggling like mad because of thermal motion. The protein is constantly going from one state, open and shut, on and off, flickering. And what the ligand does is stabilize one of the 2 states. Okay? And how does it do that? Well, by interactions between, let's say, the benzaldehyde here would interact with the benzene ring and a phenylalanine or some such, and maybe a hydrogen bond with carbonyl at the top. And those weak interactions are sufficient to tilt the balance of the receptor towards the on state. Okay? And that's how it's believed to work. So what you see is that the specificity of interaction of a molecule with a protein is due to the sum total of several, so to speak, point-wise points of contact. So in other words, here benzaldehyde would be benz plus aldehyde. Now, from this, you would deduce that there would be a pretty good correlation between shape and odor. And John Moore, who I mentioned, the 1948 guy, was the first to try and work on this. And he fastened onto the camphoraceous character as being very significant in this area. Camphoraceous, by the way, mothballs, is of no interest to perfumery whatsoever. Nobody wants the smell of mothballs. So when chemists make camphoraceous materials, which is quite often, they trash them. But to science, it's important. And these molecules are plausibly, are all camphoraceous. And Amoy said, well, look, they're all sort of spherical. Now, this is not exactly spherical, but it's sort of an honorary sphere. It's sort of flat, but never mind. It's camphoraceous. Now, when I started working in this area, this was the kind of stuff that I would read. And, you know, you get a kind of slightly uneasy feeling when you read this stuff. You think, yeah, okay. Let's see if we can find counterexamples. You know, scientists are, if you can't help, at least you can really harm it, you know? So, and pretty soon, you know, if you start looking with a sort of a negative frame of mind, you can find, let me just go back 1 second to the previous one. That fellow down there, ferrocene, is a Berger molecule, 2 5-membered rings with a thing in the middle. And you can well imagine that the thing in the middle can change quite a bit from one metal to another. Here it's iron. And you can change it to other metals, and the shape doesn't change much. Well, if you change it to nicolocene, the smell changes quite a bit, and the shape is very much the same. And if you look at this guy on the right, thiophosphoric acid dichloride ethyl amide, which I mercifully have never smelled, that, I'm reliably informed, is a camphoraceous. That is not a sphere. At any rate, it's really dented, if it is. But much more seriously, if you start pursuing this notion that let's find counterexamples to smell, there's a very nice thing you can do, which is you take a molecule which contains a carbon linked to 4 carbons, and you replace that central carbon with silicon. Now, you all know from watching Star Trek that silicon-based life forms are indistinguishable from us, slightly larger and meaner. And that's because silicon is slightly larger and meaner. And so, but from a standpoint of the shape of a molecule, replacing carbon with silicon, which you can do fairly easily, does not change the shape a great deal. What does it do to smell? It does a lot. And that's been known for a long time. And in this particular area, it's an unusual piece of work because it's been done very carefully in cooperation with chemists, between chemists and perfumers. One of the bugbears of smell research is that often the people who make the molecules aren't aware of the pitfalls like impurities and the like. So this is a proper piece of work where the Harman and Reimer, the very ancient and great company in Germany, together with Ulrich Vandergaard, who is now deceased, from Braunschweig, they made compounds in series starting from carbon, silicon, germanium, and tin. And they found differences in smell every time they changed the atom. Not just between carbon and silicon, where the biggest shape change occurs, but further up the ladder. And Vandergaard quite correctly concludes in his paper that this is a serious pain in the ass, I mean, he's more polite, for the shape theory of smell. Now, the other problem is that even the people who produce odorants, they're always looking for patterns, okay? Because, of course, you know, sandalwoods, for example. Sandalwoods are a big deal. Sandalwood oil fluctuates in price. Everybody wants to smell of sandalwood, or the perfumers use it a lot. And so having a rule for sandalwoods would be terrific. And every time the gods of fragrance chemistry have a sense of humor, and every time somebody publishes a rule, 6 months later, a molecule comes up that smells great, doesn't follow the rule. Okay? And this is a classic example of sandalwood rules. Those are the rules. And this is the one, the spanner in the works, that came along, and it doesn't. It's an alcohol, but then vodka should smell of sandalwood, which it doesn't. And it doesn't follow any of the rules and smells beautifully of sandalwood. But more specifically, this is the life of a fragrance chemist. This is how they work. They make lots of variations. Each of these things is a week's work. That's about a year's work. So a year and a fair amount of cash, and that's the only one that smells of sandalwood on this page. And including overheads, medical, insurance. Okay, so this is the reality of it. The other thing that's peculiar is why have no smell antagonists been found? Every proper receptor system has antagonists, you know, like when you go to the dentist and you block some sodium channel, or you take an antagonist to, for example, the sodium hydrogen pump in the stomach when you have heartburn and so on. why is there no smell antagonist? Why is there nothing that smells weakly of sandalwood and prevents you from smelling sandalwood for several hours? Why? No such thing has ever been. I can assure you it would have been found. It's not one of these things that you could easily pass by. You'd notice it. You smell the thing and you think, well, what happened to that other, thing? You'd notice it. Now, the question of what do receptors feel is, of course, the crucial point. There are many more odorants than receptors, naturally. Each one of those companies I mentioned has probably 100,000 compounds on the shelf. No two compounds smell identical. This is another very important factoid. Nobody, if you ask a fragrance chemist, give me two different molecules that in the pure state, in the gas chromatograph, smell identical. Never. So there's each receptor must respond to several odorants. And in fact, they do. When you do electrophysiological studies on the receptors, you find that each olfactory receptor neuron responds not to all, but to a good proportion of the odorants that you try. And therefore, receptors must feel parts of the odorant, and these have been conveniently called odotopes. In other words, this is the old elephant theory. A guy feels the tail, one feels the leg, one feels the trunk, tusks, and then they all huddle together and they say elephant. Okay? This is the idea. Now, there is a problem with enantiomers, and let me explain what enantiomers are. Enantiomers are mirror image molecules. If you have a molecule which has handedness, you can construct an exact mirror image molecule. Okay? Now, these two fellows, although they look the same to us in 3D space because we're used to the idea of mirrors, if you try and attach them to receptors, they're really quite different. It's like you try and get into your home with a key that's the exact mirror image of your normal key. Well, good luck, unless you leave the door open like some people I know. So the problem of enantiomers is interesting because you'd expect enantiomers to have completely different smells, okay? Very severely different smells, since they should bind to receptors in a chiral-specific way. So let me illustrate this. If you say that there are odotopes, so rose is made of an odotope ro and an odotope z, right? In the mirror, well, what is it? Is it going to be that, or is it going to be that? What, and for that matter, what do we smell when we smell enantiomers? Well, enantiomers should typically smell very different, but as a matter of fact, they do not. If you look at Leffingwell's database, it's on the web. He's cataloged. It's not I don't know what the statistical bias would be in this database. It's a non-random database because he's more interested in differences than in similarities, but it's still pretty good. 59% of enantiomers smell really pretty similar. 17% smell clearly different. 19% not known, and 5% identical. Okay, this is not what you would expect from an odotope-based recognition system. Okay, it's if it were shape-based, the enantiomers should really smell much more different than they actually do. And in particular, there should be no, for any decently sized molecule, there should be no cases of them smelling identical. Now, I'll just illustrate this with rhodopsin. Rhodopsin is the closest thing to olfactory receptors. It's the pigment in our eye that detects the light. And in terms of structure, we don't have the structures of the olfactory receptors yet, but we have the structure of rhodopsin. And there's a time-honored tradition in science of looking for the keys where the light is and not where you lost them. And this is one instance. People are thinking a lot about the structure of rhodopsin when they think about olfactory receptors. Now, if you look at this enantiomer problem, the molecule in gray you see there is retinal, which is the pigment that's sensitive to light. If you had the enantiomers of retinal, actually retinal is non-chiral, but that doesn't matter. But imagine you had a mirror image ligand. The whole protein would have to be a mirror image for it to bind identically. That's, of course, completely impossible. But to go back to the fundamental problem, which is as the years pass and the chemists work hard and a lot of money is spent, molecules accumulate, and they have incredibly different structures sometimes, and they fall into certain smell categories. And this is the most egregious example. This is musks. And this is basically 140 years of musks summed up in one slide. Roughly 20 years Incidentally, 20 years is the life of a patent, so it's no accident that they come up with a new one every 20 years or so. Nitromusks, macrocyclics, esters, chrominones, a funny epoxide must discovered by chance, and tetraphylline from the 50s. This is the one you're most familiar with. This is what washing powders used to smell of until a few years ago. Now they smell of those guys in the middle. You see that these molecules are extremely diverse in terms of structure. I mean, they look very different. They are very different. They smell very similar. So is molecular design by shape, smell design by shape possible? Well, I always, of course, do not believe that it is. But what I really enjoy is quoting the pundits themselves. The advocates of shape theory do not seem to believe it themselves. This is kind of interesting. The top quote is from the chemist Givaudan. We've discussed the sorry state of structure-odor relations. Funny how candid they can be. And Avery Gilbert, it is a highly empirical seat of the pants, inspired tinkering. I mean, would you go to a doctor that said this is more inspired tinkering? We currently cannot look at the structure of an odor and predict what it would smell like. Okay? This is the state of play. Now, I said there were two theories, and of course the second theory is the one that I have not invented, as some people believe, but revived, I've revived it because it was this man, this remarkable person who invented it in the 20s. Dyson, Malcolm Dyson, is known to most of us, or we actually use his work all the time without knowing it. He's the guy who invented the UPAC nomenclature for chemistry. So that when you say 6-hydroxy-2-benzyl something oxime, that's his work. He joined a committee in the 1930s that set up the UPAC nomenclature. And because he was smarter and faster than everybody else on the committee, he made up all the rules. And we owe him a great deal because they're a typically English mixture of empiricism and high principles. And he's a wonderful guy. But before this incarnation as a nomenclature chemist, he'd worked on smell. And the reason he'd worked on smell, I think, is because he was exposed to gases in the First World War. And if you're sitting in a trench and some yellow cloud is coming over the hill, smell is really the sensor you're going to focus on because it's going to tell you what's coming. And he was gassed twice and never really recovered. I mean, like most of the people who had been gassed by mustard gas, his lungs were impaired for the rest of his days. And curiously enough, his first theories on smell started with work on mustards, on the derivatives of mustard gas. And what he proposed in 1938 was that the nose was a vibrational spectroscope. Okay? In other words, that what we have in our nose is not a lock and key mechanism, but an instrument capable of taking a molecule and doing precisely what a chemist does to it. If you present a chemist, well, today he would use an NMR, which is a big machine with magnets and so on. But until the NMR came along, they would have used a spectroscope to identify a molecule. And I'll go into that in a second, how that works. So Dyson, in 38, proposes a nose spectroscope. And he did so in an article which was read at a Society of Industrial Chemistry, I think, meeting. And this being Britain, he got a polite reception. You always get a polite reception in Britain. Nobody gets very excited one way or the other. Somebody said, "Oh, this is terribly interesting. Let's move on." Yeah, the discussion is recorded, okay, of this momentous occasion. And then the story, when he lost interest, and he did lose interest, the theory went dormant, was revived by Bob Wright in the 60s, an extremely interesting guy from the University of British Columbia, an entomologist and chemist, a person who was more interested in developing smells to repel insects or attract them because of the potential implications for agriculture. And Clifton Malone, exactly the counterpart, an analytical chemist at Kansas State University in Manhattan, Kansas. Again, agriculture. One of his graduate students said to him, what is the most sensitive measuring instrument? And he, as an analytical chemist, said, well, it must be the nose. And then he looked into it, and he found that it was 100,000 times better than whatever gear they had. And he was so miffed at this, as an analytical chemist, that he decided to study smell from then on. I love that. His work has been completely ignored, chiefly because it was published in very obscure conference proceedings. It's really good stuff. And then I came along in the 90s. Now, let me try and explain what molecular vibrations are. Any molecule is made up of balls connected by springs. The balls are the atoms, the springs are the bonds. Okay? The bonds are elastic. You can imagine that if you made such a model and you kind of whacked it with a baseball bat, it would go boing, okay? Because all the stuff would jiggle. And you could also imagine, much in the way that a violin differs from a mandolin, that if you change the connections between the atoms, change the shape, the blowing would change, okay? And the idea that smell detects vibrations is simply this. No two different instruments have the same sound, and no two molecules will have the same smell, and that's what we detect. So let me show you what vibrations look like. I've translated them into hertz. They occur at 10 to the 12th factor higher. So when you start from the bottom, you see that low-frequency vibrations involve most of the molecule. And as you go up in frequency, they involve fewer and fewer atoms. And when you get past about 1800, they only involve functional groups. So let me just show it to you once more. This is SH. That's CN up there, and that's aldehyde, COH up there. And you'll see, look, CN, stretch, and then the CH stretches, okay? So what this means is that in a molecular, if you were able to smell the vibrations of a molecule, they would basically fall into two groups. The ones that involve the entire molecule, and the ones that only involve functional groups. Now, if you say this to a fragrance chemist, he would say, aha, this is really interesting. You see, because we can smell functional groups. Everybody knows we can smell functional groups. And the most luminous example of that is the fact that we can smell the SH group. You all know, everybody knows, stink bombs, that all SH compounds, known as mercaptans or thiols or sulfides, are smelly. They smell evil. No matter what you attach to an SH group, the damn thing is going to smell evil. Okay? Even if you attach a perfectly nice thing like, in this case, pinene. Pinene by itself smells of pine needles. You attach the SH and you get a hideous mixture of pine needles and rotten eggs. How many people here have actually smelt rotten eggs? I'm doing a little statistical study. Whoa! Okay. Alaska. In London, nobody raises their hand. It's really funny. People talk about, I've never smelled that. People talk about rotten eggs, and they just assume it must smell of stink bombs. Which smell of rotten eggs? Okay. I love it. So the rotten egg problem is a typical problem that will not go away in smell. You got two molecules. Picture you have the OH molecule, pinenol, and the SH molecule, pinenethiol. And that's the skeleton up there. And this is what they look like in a kind of, the electron density. Sorry, this is electrostatic charge. Okay. Now, we know from the rest of pharmacology that when you replace oxygen with sulfur, you get things which don't work as well or work slightly better or work slightly differently, but they do work. Look at barbiturates, for example. The thiobarbiturates are the thioketone equivalent of the normal barbiturates and so on and so forth. In the case of smell, vodka, unless Alaska is different, never smells of rotten eggs. Okay? Ethanol, no alcohol at any concentration ever smells of SH. And vice versa, SH always smells of SH. Okay? How can we tell these two things apart? Now, I showed this to a physicist friend, and he saw the red and the green up there, and he says, that's easy, they're a different color. Okay? But you're not allowed to say that. So when I got interested in smell, it really struck me that the functional group problem, how come we can smell SH? How come we can smell CN, the nitrile? Distinctive character. Any fragrance chemist can smell nitriles, oximes, isonitriles, aldehydes, nitro groups. I mean, how come? If you think it's an odotope, okay, these things are only going to make one hydrogen bond with whatever's coming, with whatever receptor they bind to. How does the hydrogen bond know that it's a different group? So when I got interested in this really, the SH problem struck me as really crucial. Because if you could nail that one, somehow prove that 2,500 wave numbers, which is the typical SH frequency, was associated with a particular smell, and only that, then you could start shaking the whole edifice. And what's interesting about the 2,500 wave numbers is that there's a kind of a little vibrational desert on either side. Nothing much vibrates above 2150 and below 27 something. So there's not much in that area. And in fact, until I started looking into it, there was nothing known, really well known in that area. I started looking at the literature, and it turned out that there was a class of compounds that did vibrate at that frequency, and they're called boranes, BH compounds. Boron is west of carbon in the periodic table, and it bears no relation chemically to sulfur at all. It's trivalent. Now, boranes are interesting compounds. They were first made in the 1910s by Alfred Stock, and they have interesting properties, like they spontaneously ignite when exposed to air, and they make a bright green flame. They're used to start rocket engines, and they're generally quite nasty. And when I called up the firm that makes borane propellants here in the U.S. And asked their chief chemist. I was kind of a little cagey because he's wondering why a physiologist from London is calling him up about rocket fuels. Okay, so he thinks we got a kook on the line here, you know. So I say, can you send us a sample of a borane or two? He said, no, we only send minimum 10 tons. So I could see this was going to be uphill. So I said, well, what do they smell of? And there was this long silence. He said, what do you mean? I said, well, what do they smell of? And he says, sir, I try never to smell them. And that was all he would say. So then I started asking around, and eventually I ordered this stuff, which you can find in the Sigma catalog. Remarkably, you can have it tomorrow morning if you, well, not tomorrow morning, but the day after. And I smelt it, and it smells beautifully of SH. Okay. It smells of boiled onion. And then I started asking chemists, you know, borane chemists, and I would say to them, isn't it amazing? They smell, oh, yeah, of course, they all do. We all know that, of course. So it's been known since forever. And in fact, Alfred Stock himself, who got the Nobel for all the boranes, purification of the boranes, noted it in a huge, long German paper. Surpassingly unpleasant smell, not unlike H2S. There you are. Extremely repulsive, also reminiscent of hydrogen sulfide. He goes on and on every time he says, revolting, disgusting. Now, the problem with the spectroscope theory is really very simple, is that this is what a spectroscope looks like, okay? And it's a large object. And if you look up someone's nose, you see nothing resembling And really, there are some basic structural requirements to an optical spectroscope, which is an infrared light source, a light detector, all sorts of things which do not agree with biology because infrared is intensely absorbed by water. We are made of 80% water. End of theory, okay? And this was the problem that first Dyson and then Wright had, that everybody would listen to these wonderful correlation between vibrations and smell that they'd come up with, and they would say, yes, that's all very well, but how does it work? Okay? How does it work? What's the spectroscope? And Wright had no answer to that. And it's a shame he didn't have an answer because Wright, so to speak, probably a few meters from him was a paper, not in an obscure journal, but in Physical Review Letters, which had he known about it, I wouldn't be here telling you this today. Because the method for making a spectroscope without optics had been developed in the 1960s by two guys at Ford Motor Company. And I know that Bob Wright would have understood this instantly had he known. And I also spoke to these two guys who developed it, and I asked them what the story was. And he said, well, we discovered this way of measuring vibrations without optics. And John Lamb, one of the two, said, maybe that's how smell works. And I'm sitting on the phone to this guy, and I say, that's pretty clever. And he says, yeah, we're smart. We're physicists. I love that. And what happened was they went to see a chemist down the hall, and they said, look, we got this spectrum. We were wondering whether smell might work like that. And the guy said, nah, it's shape. And they went back to their office and forgot all about it. So, and that was 40 years ago. So what did they discover? They discovered a thing called inelastic tunneling. So this is an electron jumping from a full to an empty energy level, but it must do so at equal altitude. So in order to jump when there is a downward jump, it must lose some energy. Okay? This is a very important concept. So here you have the electron top left. It's going to go along its own energy level, and it can't jump down because it can't lose the energy until something comes along that has the right boing vibration, and then it can flow. Okay? So this is what's called indirect tunneling, and it's by the way, I do not understand it any better than that. Okay? Don't get the impression I'm giving you the simplified version. I'm collaborating with physicists who work on this and who just submitted a paper to Physical Review Letters, and they sent it to me for comment. And I sent it back the same day saying, great. Best paper I ever read. It's the actual solid-state physics is pretty arcane in the sense, but it boils down to a very simple principle, which is that in quantum mechanics, it's a little bit as if before doing a ski jump, you telephone down at the bottom. You can't see it because of fog, and you telephone down to ask if the area is clear. Okay? If a particular jump of an electron from A to B can only occur if both A and B agree. It's not like in classical mechanics where you say, the hell with it, I'll jump and we'll see who's down there. It only works when the whole process is smoothed out. And therefore, if you have a jump in energy, it will only take place when the molecule can absorb the energy in the middle. And therefore, this is what amounts to a spectroscope in the sense that imagine that you have several classes of receptors tuned to several different heights of the jump. They would be then like the pigments in the eye. You could have a class of receptors that explores 2300 to 2600, one that does 1800 to 21 or something like that, and then you add up all the signals, and the point in odor space tells you what the smell is. Now, this, if you go into the biology of it, and I will in a second, none of the bits and pieces of this mechanism are implausible. Okay? There are plenty of enzymes that transfer electrons in biology, in mitochondria. Oxidoreductase is a cross-cell membrane, so there's nothing fancy about any of it. So to give you an idea of what the transduction might look like, this is the new and improved receptor spectroscope. The benzaldehyde attaches, an electron flows through, and releases a G protein by, let's say, breaking a sulfur-sulfur bridge or some chemical reaction of that order, which depends on electrons. So this is not in any way, shape, or form a proof, but it's a plausibility argument. But it's interesting that something which was considered completely insane, okay, the spectroscope in the nose, can turn out, thanks to a piece of work done at Ford Motor to work on ball bearings, turn out to be not so insane after all. This is how science works. You just never know where it's going to come from. Now, how does one test such a theory? Well, the easiest way to do it is to change vibrations without changing shape. And to do that, you replace all the hydrogens in a molecule with deuterium. Okay? And deuterium is indistinguishable from hydrogen in most respects. It has a heavier nucleus. And the nucleus is buried in the middle and cannot be felt from the outside, so you don't know that it's heavier. And this has been done, so molecular shape unchanged, and vibrations will be changed. And you can do this objectively on a zebrafish olfactory bulb. That is to say, you measure the response to the olfactory bulb of a zebrafish, which is a small fish, very popular among biologists, because you can do genetics. And you expose the beastie to odorants at exactly the same concentration, and you look at the different responses. Do they respond differently to the isotopes, yes or no? Well, the answer is yes, otherwise I wouldn't be showing you this. Response to normal molecule, that's the time course of the response. Response to the isotope, and it'll look very similar. But because you can do this 20 times with the same concentrations, you can subtract one from the other. And The difference between isotope and normal is non-zero. Okay? That means there's a difference. And if you subtract them the other way, you can show that it's not just a change of scale. Some things light up in one that don't light up in the other. Okay? So here you have evidence from, proper measurements on brain cells that the fish can tell isotopes apart. Of course, we knew that because these things can smell the isotopes. If you train them to do one task with lysine and another task with deuterated lysine, they learn that. So we knew that behaviorally, but this is a better test. Humans can sometimes tell isotopes apart and sometimes not. And the trouble, this has been one of the difficulties with my theory, which is that humans have a lousy sense of smell and don't pay much attention to it. And so that if you want to design human experiments, you're starting completely at the wrong end of the animal spectrum. Something that the dogs can do in a flash, the humans can do only on a good day. Okay? And the balance of evidence on humans has been about 50-50. Okay. I'm going to finish off the last 10 minutes on how I've been using this theory to design new molecules. But I'd just like to reflect for a second on what happens when you propose a new theory and how science proceeds. Well, the answer is I really do not believe in conspiracy theories. I really do not think that there is a sort of an active organized resistance to novelty. After all scientists must at some level love the new, at least one hopes. Otherwise, they wouldn't be in that game. But what I do believe is that in situations where you are doing interdisciplinary work, you never get in the same room the people who could discuss with each other what's wrong or what's right about a particular theory. So in this particular instance, you have a theory which is half physics, half pharmacology, 1/3 physics, 1/3 pharmacology, 1/3 biology, whatever. And you never get a quorum. You never get the fragrance chemist talking to the solid-state physicist talking to the biologist. And this is a difficulty which has nothing to do with their own individual attitudes to science. It's simply ignorance, which is perfectly human. So, but it is a problem which really has hampered the development of science in the last 20 years, which is over-specialization. That you no longer have what used to be around, like someone like Enrico Fermi, somebody like that, who was the honest broker. You would show him anything. He would eyeball it, and he would say, this looks okay to me. And that was it, you see. And now you only have specialists. Anyway, I don't want to harp on this, but I think it's a very fundamental problem in the teaching and the practice of science. So what have I been doing the last few years? Well, some years back, I was getting pretty miserable at University College, not because it's a bad place, but because the tendency for when you turn 45, 50 is that you're supposed to accumulate a large lab and get a lot of people and get a lot of money. And I've always enjoyed tinkering. I was brought up in a sort of good old-fashioned British string and glue approach to science. An empty room, 2 bits of wood, go forth. And in contemporary universities, this becomes harder and harder to do because you're basically not bringing in the cash. And so my life was getting increasingly difficult. And you know that because you're doing more and more teaching. I love teaching, but it's used as a punishment in British universities. And so one day, a venture capitalist from the U.S. turned up, a friend of my wife's turned up at dinner, and I told her that I'd done a consultancy for Guinness, for the beer people, and they asked me about an acid-stable lemon. Could I make an acid-stable lemon? And I thought about it for a few days, and the answer was yes. I think from vibrations I could probably calculate an acid-stable lemon. And she, being a U.S. businesswoman, with the brains fully turned on, even with jet lag, she said, do you know what? That sounds like might be a business in there, And she said, do you have any objections to me finding large amounts of cash to put this to the test? And what she did was she found a reasonable amount of cash, and we did the synthesis of that one molecule. And she said, if it smells of lemon, I believe. And it smelled of lemon, and it was acid stable. And that's how we started. And I'll just show you the kind of stuff that we do. Sorry? No. It's really funny. What happened to that? The guy who was in charge of R&D, this is the dreadful thing about big corporations. They say, go find us. You come back 6 months later. The guy's been moved to Venezuela. Guinness went through 4 management reorganizations in a year and a half. And each time, they changed all the phone numbers and all the people. So in the end, we gave up. We sold it to someone else. So one of the things that we've been doing is in response to an entirely spurious obsession in Europe with allergens. Europeans, having nothing more severe to worry about, have I'm absolutely serious. Now that the Russians have gone, the allergies have come up, okay? And a bunch of politicians in Europe are making a very good living out of scaring the pants off people, telling them that when they put on Chanel 5, they're going to get scrofula or whatever, leprosy or something. And so they've restricted the use of 29 of the most common, 26 of the most common fragrance materials. And it's a pure statistical fluke because those materials are the ones that were most commonly used and therefore have created enough people in the dermatologist's waiting rooms that you'd notice. Okay, there's no real, those aren't special materials, it's just common. So they take the 26 most common and they say, you can't use them anymore. Okay, so the perfumers say, okay, we'll use something else. But the people the marketing people say, wait a minute, you can't change Dove. You know, that smells good. You know, you can't do that. So there's a market for replacements. And we've been making replacements. And I want to emphasize that what we call a replacement is something which is not on the list. It will be. But by that time, we'll be retired and rich. And it doesn't matter. So one classic allergen, perfectly harmless thing, really. It's as if you declared aspirin to be an allergen, you know, and then you got to go and find something else. An EU allergen, hexosinamic aldehyde, smells of olive oil, very important floral molecule. And we made a very nice replacement for it using, if you look at that 6-membered ring, that benzene ring, we use a 5-membered ring with a sulfur in it. And it smells absolutely beautiful, more powerful, more durable, very cheap to make. Chemists always stayed away from this because when they see that green, they think the devil. But ignorance is wonderful. You do things you... No. Eventually you'll become allergic to that. But and another one which we were asked to do was a coumarin. We had this wonderful French perfumer who listens to all, you know, this presentations on the previous molecule and says, "Oh, I bet you cannot do a coumarin," you know. And my boss has a love-hate relationship with Frenchmen, so she comes out and says, "Oh, I bet you we can do a coumarin." So we tried to do the same trick with coumarin by replacing a 6-membered ring of coumarin with a 5-member with sulfur. And the good news is it does smell of coumarin, but the bad news is it's totally unstable. Chemically, an absolute disaster. So we were stumped, and then the vibrational spectra, of course, match, which is how we do the prediction. You see, what we do is we do in whatever, they call it in silico, which is probably really bad Latin. We calculate, we take a structure, we calculate the vibrational spectrum, we look if it matches. If it matches, we make it. If it doesn't match, we don't make it. So we weed out the structure tree enormously. So we're very efficient. And so we were stumped by this one until my chemists called me up and say, I found this wonderful structure. Wonderful thing. 2 steps, 80% yield. So I said, and? Said, well, look, it's got that thing. It's got that sulfur thing next to the lactone ring that you asked for. Oh, okay. So I calculated it, and it looked pretty good. I said, make it. And you will see that this molecule has 3 rings instead of 2 and completely bent out of shape with respect to coumarin. But when you look at the spectra, beautiful. So I thought, okay, let's make it. And if you look at the vibrations underlying the spectra is smooth. They're not the same. They add up to the same when smooth. It's not that the vibrations match each other point for point. They convolve in the same way. So for example, there's a big vibration at 761 in coumarin, and there are 3 vibrations in the other molecule whose amplitudes add up to that. So it's not something you could do on the back of an envelope. And you see, that's the shape change, and that's our product, Tonkin, which really smells coumarin. You know, the perfumers love it. But it's very non-volatile. So that's because it's heavy. So this is the kind of stuff that we've been doing. And in fact, we found a new one now, which is this guy, our latest product, with a 3-membered ring instead of the double bond. And that also smells of coumarin. So this is the kind of fun that I've been having the last 4 years now. And we've picked out, you know, the allergens. I mean, this is half of the EU list of allergens plus quite a few others. We picked them out one by one. And at first, everybody thought, they're just lucky. And after a while, they started thinking, why don't they go away? And now they think, how can we get these guys on board? And now we're working with all the big firms. And the way it works is, it's a little bit like gays in the military. Don't ask, don't tell. Nobody mentions theories. You come with a 5-gram bottle of something. They don't care if you got there by astrology. And it's a funny sort of limbo at the moment. But it's fine. I'm not complaining. We're having the fun of a lifetime. That's all I have to say tonight. Thank you very much for coming. Please ask questions. I don't think, I think I had an interest in perfumery. I just liked perfumes. I liked the perfumes that my mother wore and that sort of stuff. And I started collecting fragrances in the days when it was very cheap. But mostly, it was the gradual realization that this was really unsolved that got me sucked in, even before I started working on it. It was, you know, people, if you read the scientific literature, people never say what they don't know. And so you only infer it. It's a bit like a family secret, like Uncle something did something really bad in 1932, and nobody ever talks about it, but there's a kind of uncle-shaped hole somewhere in the conversation. And after, I guess that's what happened with smell, that after a while I realized that the bits didn't add up. And by that time I had enough experience of smell itself, of smelling raw materials and molecules because of the perfumery side, because I was writing also, I wrote a guide to perfumery, to perfumes, and I had enough confidence in what my nose was telling me to know when something was manifest nonsense. Yeah, new cardboard boxes smell wonderful. You see, there's a wonderful thing that people, that we associate smells with things. And so that, if there was a flower that smelled of cardboard boxes, it would be classed among the florals for no particular reason, okay? But if it's only cardboard boxes smell of cardboard boxes, then you associate it with something very functional and lowly. So when this perfume came out called Zing that smells of cardboard boxes, I was bowled over. I thought it was the most wonderful thing in the world. That something so trivial could be turned into fine fragrance. It was just high art.
Are there counterexamples to the vibration theory? You talked about counterexamples in shape early on.
Yes. Well, the question of isotopes, I mean, to be honest, I think isotopes should be more different than they are. Okay? So when you do an experiment with isotopes, even when you can smell the difference, it's not that big. And I don't like that. It's there. But I would much prefer it to be much bigger. So right now we're trying to identify isotope pairs that have the biggest possible difference and trying to understand what the difference is between those that do and those that don't. So that's a sort of a counterexample. It's not quite a counterexample, but it's a problem, okay? And the other thing is that's absolutely clear is that this theory does not predict intensity. You know, there are strong roses and weak roses. And once you say spectrum, you've said precisely nothing about intensity. And it's absolutely clear that intensity of an odorant has everything to do with shape. Okay? So that the way it looks right now is the theory is split right down the middle. Odor character looks like vibrations, and odor intensity looks like shape. And that makes very good physicochemical sense, because shape is binding affinity, ultimately. That's right. No, it's in your DNA, okay? In your DNA. There are 347 copies of an olfactory receptor gene, okay? So that if you look around the body, you will find that the olfactory receptor neurons, each neuron expresses one of 347 receptors, okay? However, it's not quite that simple, because you will find olfactory receptors in the weirdest places, okay? In the heart, kidney, okay. What are they doing there? Nobody knows. But so out of the 347, fully 40 or something are totally in the wrong place. And the remaining 300, however, are properly in the nose. Yes, very much so, yeah. Oh, there's been a tremendous fashion, you know, for fruity things. And yeah, it's... Any reason for that? Perfumes for the last 10 years have been made for people who don't like perfume. 10, 15 years. The young who think that Mummy's big Estee Lauder thing stinks, okay? So you start from, it's like making music for people who hate classical music. You're not allowed to use cellos. You're not allowed, you know, you're trying to stay away from certain things, and then you're left with skimpy little florals. Fruity.
Has work been done looking at existing mimics of odors to support your theory? In other words, you know, you have one point you put up the diagram there, you know, the pot shot approach where they were able to find one that mimicked what they were looking for. Have you tried to apply the theory to those?
Yes, you can download from the Flextral website. There is an early attempt by me at classifying known odor characters using computational methods. And it's called Prediction of Odor Character from Structure, the article. It uses old-fashioned computational methods. One of the downsides of being in the private sector is you can't really tell people what you're up to. But that's as far as I went before I joined the company. And you can download that from the website.
Why do things smell bad to us and some things smell good?
Okay, sorry. The very few bad smells are hardwired, okay, in my opinion. I'm not a psychologist of smell, but it strikes me that there are some things you want to avoid as a matter of course. Putrefaction in general produces amines and sulfides. Nobody likes sulfides to start with, okay? We get used to French cheeses and stuff like that. And people eventually like the durian fruit. Are you familiar with durians? Durians are a big Southeast Asian fruit which contains mercaptoethanol, I think, or some sulfide, which smells incredibly vile. And yet, when you get up close, strange, you get used to it. About 10, 15 minutes, you're eating it up, and there's no problem. So I think very few things are hardwired. I think everything is pretty much cultural. Yes, you can. And the results are disturbing, because when people measure from single olfactory neurons, they find, as I said, that the neurons do respond to a reasonably broad spectrum of odorants. The problem is the concentrations used are really high. Very few of the studies use concentrations of odorants that seem reasonable considering what we can smell. The jury is very much still out as to whether the electrophysiology studies on single olfactory receptor neurons are a meaningful physiological thing or not. And I'm sorry to be kind of depressing on this, but it's really, really difficult to understand what those things mean. But yes, you can do single unit recording. There, again, it's hard to say. I mean, people have tried to express olfactory receptors in non-neuron cells, to do heterologous expression. They don't seem to work very well. They don't seem to work at all in most cases. There's clearly something funny. I think a lot of people at the moment are thinking, and I think it's wrong, they think that for each receptor there is a magic odorant which will work at very low concentrations, and the trick is to find it. I don't see that. I don't see that working. We have 340 receptors. They do respond to different things. Suppose you find something that they're much more sensitive to. What have you shown? It can't be one receptor, one smell, since there's so many more smells than receptors anyway. So I'm not sure which way the field is going to pan out. The other animals, as far as I know, tend to have more than we do in terms of numbers of receptors. Why dogs have such a good sense of smell is a big mystery, in my opinion. I mean, Richard Feynman always say, well, that's easy. They have their nose closer to the ground. And it's funny because it's a whimsical answer, but there may be some truth in that. Because if you think about it, imagine you take a bunch of cells with a given receptors with given sensitivity, okay? And you increase the size of the epithelium. You're not going to increase sensitivity necessarily. It's like having let me make a comparison with film. If you have a 400 ASA film and you take the size of a double bed, you're not going to pick up really that much more light necessarily, okay? So why are dogs so damn good at smelling things is still pretty much a mystery. Yeah, and also, absolutely, and very interestingly, have you noticed how incredibly indifferent to perfume they are? If you spray perfume on your hand and you put it under a dog's nose, nothing. And yet, they'll go and smell a lamppost for half an hour. Yes. Well, that's a really fundamentally important question. I mean, the odorants, because they're hydrophobic, because they are oil-loving substances, are capable of entering membranes and entering proteins even, diffusing into the guts of a protein. There's nothing really preventing a water-soluble odorant from doing so, provided that the channel to the spot where it wants to go is lined with hydrophilic groups. But the truth is, it's not entirely clear whether olfaction of marine or of water animals is really the same. It should be, because the receptor sequences are close, okay? Is it exactly the same mechanism? Those lysine experiments, of course, would suggest there is a commonality, since there's an isotope difference. And is olfaction the same as taste? Is it the same mechanism as taste, which is our waterborne thing? And there, all bets are off, because if you think there are problems in structure-odor relations, you look at structure-taste relations, it's awful. I mean, the sweet, for example, if you look at this range of substances that are sweet, it's a nightmare. Yeah, and this is an interesting point. This is a point that my colleague Marshall Stoneham, who's a physicist, makes. He says we've become so used to the idea of lock and key that nobody asks what turns the key, okay? And that there may be a hell of a lot more to pharmacology than we realize, in the sense that there may be many situations where the analogy would be a swipe card, that the receptor reads the molecule somehow, either with this sort of electronic solid-state mechanism or by electron transfer or some other stuff that we don't yet know about. And of course it has to fit. Of course the swipe card has to fit. You can't do it with a plank, okay? But that's not the whole story. And I personally believe that Marshall Stoneham is right, and that the next 20 years in pharmacology will see the other half of the story, you know, beyond the sort of lock and key idea. You know. One more question, I think.
Is a human sense of smell pretty universal, and you find differences?
The differences have been vastly overplayed. Okay, most people have a good nose, unless there's a mechanical hindrance to that. Most people don't have an abiding interest in smell. Those that do use it mostly for food and cooking. That's what smell is mostly about. And differences in perception of aroma chemicals are extremely rare. When the classic one is phenylacetic acid, where 50% of people say honey and 50% of people say pee-pee. Okay? Now, if you smell it, it smells of both. So that it's like turquoise. 50% will say green, 50% will say blue. Well, what's the big deal? They're smelling the same thing. There are one or two aroma chemicals, really unusual things. Caranal is one, which smells ambery, woody to 91% of people, and urinous to 9%. Now, there's no way that the two groups would agree with each other. Okay? No. Well, women. The 9% are all female. Ethnic difference.
Well, I'd like to thank you very much for spending some time on your vacation.
Thank you.
To talk.
Thank you.
And